Good morning, everybody. Welcome for another seminar at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Sebastián Sánchez from UNAM in Mexico, and he will talk about the local volume mapper state of the art. Sebastián will be introduced by Rosa González. Please, Rosa.
Okay, good morning. So I will change to Spanish because I want to first to introduce Sebastián. I would like to say que hoy es el Día Internacional de la Poesía y antes, pues, puesto que tenemos en la sala un poeta, pues me gustaría que él pudiera recitar algunos de sus poemas antes de comenzar el seminario. Bueno, deciros que Ginés tiene publicado un libro de poesía que se llama El tiempo y el tiempo, que, bueno, estamos muy familiarizados con el tiempo, tanto a nivel personal como a nivel astrofísico, y bueno, él nos va a dar ahora otra perspectiva, que es la perspectiva de los poetas.
Bueno, voy a hablar del tiempo, es un poco muy cortillo, solamente para introducir aquí, ya que estamos en Granada y que se va a quedar aquí en Granada, pues voy a leer este poema de Granada y ya luego con usted. Dice así: sobre un valle reposa la ciudad que en amarillo soleado reluce siempre de azahar tejado y verde mariposa. Sentado sobre el valle, sus venas azules cristalizadas cubren los montes entre los que yacen árboles de granada. Olivos en tempura verde oscura, almendros de espumosa nata suave, y entre ellos su gente, en eclosión diurna, comparte el sol que en oro se deshace. Del invierno al verano de repente, de día de estrella a noche de luna, reemplazamos las pieles por las plumas, volamos en sabor de golondrinas, nos contamos los cuentos de la Alhambra en el flamenco de un gorrión que trina sobre palmas de patio y de guitarra. Siempre álgida la polis capital, la reina de las taifas, la corona del reino, coloreada en gracia por sus pueblos, la joya del imperio, acostada en la falda de la sierra más alta y más nevada, allí entre el Darro y el Genil, entre el cielo inmenso y el Albaicín, yace hermosa, la ciudad de Granada.
Precioso.
Después de esto,
os recomiendo que si tenéis oportunidad, porque leáis su libro, El tiempo y el tiempo. Es como un libro de cabecera que hay uno, pues, cada noche o cada mañana, si quieres, puede gozar de lo que es capaz de hacer con palabras. Okay, let's start with the seminar today. So I would like to introduce to Sebastián Sánchez. He has already been properly introduced last week by Isabel in the Severo colloquium, but today I will try to make a big summary, well, a summary of his CV. Well, Sebastián is right now at the Universidad Nacional Autónoma de México. He is equivalent to the profesor de investigación at the TESIC, investigador titular C. Previously, he got his PhD at the University of Cantabria, and he was a postdoc at the Calaralto, and also they got a Marie Curie at the Potsdam Institute in Germany. He worked also at Fecha and was also a Ramónica Hart here at the IA UNAM. Well, he is the main focus of his research is to understand the evolution of galaxy using integral field spectroscopy, and he has been the PI of the Calipha project. In this project, they participate more than 80 scientists from 20 countries, but he also has contributed significantly to another integral field spectroscopy survey at Manga, Sami, and Musi. In terms of publication, they had a lot of record. In particular, it is it is the second person in Mexico with the larger exhibition in the physics area. And also, he has published more than 600 papers with more than 24,000 citations. And they have been invited and write one of the most prestigious paper or the journal, which is the annual review of astronomy and astrophysics. He has also supervised a PhD and also has a lot of experience in the in teaching activity and graduate students. Finally, to mention that he has also researched or has developed a lot of software for the analysis of integral field spectroscopy. And today, in fact, he's going to talk about a new project that he is working, which is the local volume mapper. So, please.
Okay, so thanks a lot for the poem. I'm really honored. And for inviting me. This has been a tremendous productive month. Coming back like to home to me. Coming to this place. And I'm going to present you a tiny project that we have been working in the last. Actually, I don't remember when we started to do that. From the ideas to the ground. The project is named the Local Volume Mapper. It's one of the 3 mappers of the Sloan 5. And just to tell you that this is something that is on cookie, no? It's not finished, and there's early results, and we have more problems than more questions than answers. I want to highlight the contribution of these people that are key to the project. The PI, Smith Drury, Guillermo Blanc, that he's basically the person that is managing all the construction and the infrastructure, and Evelyn, it's tracking on the observations, and Catherine is really the one that is pushing more on the science. Just to tell you how young is that. This picture was taken in the October 2022. That's the spectrograph was still not well. It's one of the units of the 4 units that compose the I will not name instrument. Let's say instrumental setup, because it's quite different of what we have handled before. And we meet there just to see how it was. This picture was taken the integration of the first integration of the 4 units that configure the instrumental setup. This was in March of 2030, so 1 year ago. Commissioning didn't start until summer. We didn't finish to assemble everything. And early signs was observed in September and October. And we have still not finished the reduction, the data analysis pipelines. And we are observing, we have the clearance for observing by the Sloan by the end of October. So basically, taking data, real data on the project is just 4 months, and we still have a bunch of problems that I'm not going to hide. I'm going to show you in here how we really are. So what is the local volume mapper? The local volume mapper is a completely different thing of what have been embarked before, and somehow it's also very similar. We want to observe with an integral field unit the Milky Way. So if they give us enough time, that the bus/money, we will cover all the entire Milky Way with this IA field. Of course, they didn't give us time/money for doing that. We want to select also the galaxies in the local group and the local volume, understand the local volume, basically from here to Andromeda. And for sampling Andromeda, we lack of the resources so far, because we need another instrumental setup that should be built in the north. So today I'm going to talk about the south. The local volume mapper is the first IA field survey that is going to sample a bunch of the sky in a blind way. So it's going to sample everything that can be observed. Now we are going to, it's a tremendous size. It's more than one stereo radian, what we have foreseen just for the Sun. So we want to observe our galaxy and not to make cherry picking. So basically observe everything in a continuous way. So the old approach from IA Fuse, but apply to our galaxy. And the focus of this survey is on feedback. And I'm going to try to tell you why I think and why we think feedback is important. And this connected with the talk I gave last week or last week. It's tremendous thing. We want to observe different structures with different projection size because as you share in our galaxy, as more far away is an object, as worse is the resolution, as near is the object, as better is the resolution. So sampling everything, we will sample different scales from the order of the parsec to the entire galaxy. So we will cover from a few parsecs to a few hundred parsec to 1 kiloparsec to entire galaxies. With that, we will try to give the information that is required for understanding feedback at very different scales. So what we knew before starting local volume mapper, this is a connection with what I presented before. There has been a lot of development in the last 10 years, I would say, in the exploration of galaxies, especially resolved using integral field units. This is an example different of the one that I presented the other day. This is a distribution, the star formation rate versus stellar mass, integrated global quantities for the galaxies in the MANGA survey. So there are 10,000 galaxies shown in here. They are sampled at different apertures. That's connected with my previous talk. The plots are very, very similar. So here we have a continuous map, and as you can see, the bluish galaxies. This is RGR, so it's basically sampling the stellar population. The star-forming galaxies that are bluish are located in a very tight relation that is known as the star formation main sequence. If we show the emission lines, I mean here emission lines are shown in the same picture, in the same colors I told you the other day. Oxygen 3 is in blue, H alpha is in green, and nitrogen is in red. So it's a kind of BPT diagram, spatially resolved. And the strongest emission lines and the ones that are more dominated by greenish colors, that means a strong H alpha, are the ones that are located in this star formation main sequence. For the ones that have a good eye and a better understanding of metallicity, and for instance, Pepe obviously will notice that here are more bluish and here are more greenish, and that basically tells you that there is a chain, primary chain in metallicity with the mass that is telling about another integral global relation, the mass metallicity relation. If you compare the kinematics, most of the galaxies that are in here are mainly supported by rotation, and the galaxies that are in here are mostly supported by random motion. It's not random motion, actually, it's just the orbits are they don't share the same angular momentum. That's the real meaning of that. And if you explore the age of the stellar populations, the galaxies with younger stellar populations are the ones that are in blue here, are the ones that are following this type relation. So this was uncovered by these IA Fuse surveys, this massive survey using integral field spectroscopy. With that surveys, we were able to resolve galaxies to a kiloparsec scale and uncover the ionization at different locations in the galaxy at this scale of 1 kiloparsec. That was the focus of my previous talk. One of the things that emerged from that surveys, and this is the connection to lower scales, is the fact that the global extensive relations that are the ones that are highlighted here, the star formation main sequence, the spin chemical law, and the mass, the molecular gas mass sequence. All these relations that are fulfilled for star-forming galaxies, they have a mimic or a counter relation at the 1 kiloparsec scale, and that relation at 1 kiloparsec scale that it's shown here in yellow. These are points of different galaxies taken from a survey named EDGE that map the galaxies of Khalifa. Each point in here is a region, and star forming region in very different galaxies. And the star formation surface density correlates with the star formation. Star formation surface density correlates with the surface density of the stellar mass. The star formation surface density correlates with the molecular gas surface density, and the molecular gas surface density correlates with the stellar mass surface density at the 1 kiloparsec scale. The curious thing is that when you take these global relations and you transform them to intensive but also global relations, dividing the extensive parameters by the area, and that's what is highlighted here by these two lines. Repeat that for the entire site of Khalifa and for the center part of Khalifa using these observations of CO taken by Apex. The relations that you obtain, and that is highlighted here. In here, contours means one galaxies. So it's the density of galaxies, and I repeat, the yellow points correspond to spatial resolved structures within galaxies. The relations that you get for entire galaxies in the intensive form and the relation that you get at 1 kiloparsec scale follow exactly the same kind of relation with the same shape and the same slope. This is telling us that what is driven or controlling star formation, the rules the laws that rules star formation are fulfilled at scales that big as a galaxy and a scale that small as 1 kiloparsec. So one question that emerging here is how low we have to go until these correlations breaks, because the people that have been working in star formation at the site of molecular clouds and below, they know for a long time ago that these relations really are not fulfilled when you are sampling size of 1 parsec. So again, thank you for my previous talk. There are people that have explored that. I want to repeat that. This is a very interesting exploration where they have taken images of the same galaxy in two bands, one sampling the molecular gas. It's a CO observations, this is in blue, and another taking an H-alpha map that is here in red. And the experiment they did was, okay, I'm going to take the peaks of intensity in the map of the molecular mass density, and from there I'm going to take different apertures, and I'm going to make the ratio between the amount of molecular mass that I see there with respect to the amount of H-alpha, or so basically it's the gas to star formation rate as is expressed here. So when they are at the very low scales, these small apertures, the ratio departs from the expected value of 1, that would be more or less the value that you expect from the Smith-Kennecott relation. As the apertures enlarge and enlarge and enlarge, and when you go in the regime of 500 parsecs to 1 kiloparsec, this converts to 1. On the other side, if you repeat the same experiment, but you start in the peaks of H-alpha, you have the opposite trend. So you have a value that is far from the relation of 1, and then it converts again to 1. So in this regime is where we have explored galaxies with IFU surveys, like Khalifa and Manga. The Khalifa will be like here, Manga will be like here, but anyway, it's the same regime. And in here is where you start to explore galaxies, in particular in this regime here, with things like fangs and signals that are more recent IFU surveys of complete but more nearby galaxies. And those surveys already have reported that they have a variety in these relations, and they cannot confirm the existence of a tie relation that we have seen before. And that means that there are scales where these relations break. So the puzzling here is why there is a relation, why there are scales where this relation exists, and why there are the scales where this relation does not exist. So we require to explore this regime here. But we have made experiments of trying to hint what's the origin of this relation, and why most probably what most probably a physical connection between the quantities that we are exploring here. So one of the main lines of exploring these relations is trying to know if there is a prevalence between them. So which one of them is the primary relation? If there are secondary relations, saying like, for example, if this is the primary relation, the other can be explained as a secondary relation of these two. So that means that it's not a relation between two parameters, but it's a surface in the three-dimensional space. Or if there are a hidden parameter that connect the three relations into one. So the line of paths goes more in this second approach. And the three relations, they don't seem to be a surface in the three-dimensional space, but a line in the three-dimensional space. It will be something like that. You know? So just think about that. The surface, you can see the surface projected in a three-dimensional space as a relation between two parameters. But if you don't have a secondary relation between the residuals of the one relation to the other parameter, what you have is a line. When you have a line, that means that there is a hidden parameter that you will love that, you know, it's a kind of a hidden parameter that could be pinned up with these machine learning techniques that explain the three other parameters at the same time. So in this exploration, there have been several advances. I just show here some of the ones that we are involved. Like for instance, if you combine the molecular gas and the stellar mass surface density in some kind of mathematically driven way, you can find a relation that is tighter than any of these two relations, and at the same time is not describing the surface. So it's some kind of a line in the three-dimensional space. So star formation rate is related to these two things. But if you go to these values here and go back to the literature, and there is a lot of literature about that, even in the 70s and the 80s, this is a hint of the pressure, you know? So the pressure that is supported by the molecular clouds in a disk of a galaxy can be written by a combination of these two parameters, assuming make a lot of things. And in this line of thinking, there were some people like Stryker and all her school that has already proposed a relation between the pressure and the star formation rate. And the reason for this relation could be the feedback. So star formation generates the feedback, and this feedback regulates the star formation itself. It's a kind of self-regulated process. So this line here, it's more or less the line that was proposed by Stryker, and this is the values that we took from one. If you want to see more about that, there is a more recent article by Sarah Harrison, where she already show a hint. You may see that there is a kind of flattening here. And when she explored that in more detail, the flattening was more evident using the data from AlmaQuest. And she proposed that there are two regimes of the pressure, but in any way, the connection is essentially the same. You know, it's a self-regulation of the star formation. If this happens, when you talk about self-regulation, automatically you are talking about a time scale and a velocity scale. And that means a height scale. So if you more or less assume a certain range of velocities for any kind of outflowing or a gas moving in a galaxy produced by a star formation, ejection of energy by a star formation, and you assume a certain time for the star formation process to be seen, and this is a typical time scale of an H2 region, automatically you will have a physical scale. And which physical scale is that? Of the order of 500 parsecs to 1 kiloparsec. So this idea, it indicates that feedback, it may be one of the drivers of the relations that we have seen before. Okay, so with that on mind, the problem is that we have a general idea about feedback, but the physics of feedback is far from being understood. Okay, And that's what we started to do. We started to work on the local volume map, because how the physics happens, at which scale the physics happens on the star formation, is a much smaller scale than the scale that we have explored before with IFU surveys. So even if we have a hint of the connection between the feedback and the relations that we have seen at the kiloparsec scale, we still don't understand completely the physics. So the physics, and I'm not going to make a summary of what's going on here, that's for master classes, but you know that the physics that were at the scale at which star formation happens may range from just the size of an individual star, the size of an individual molecular cloud, an H2 region, or just the size from several H2 regions to the size of the galaxy. And we need to connect all these scales if we want to understand feedback. So with that in mind, and with the driver, the focus on feedback, what we want to understand, or what we think we are going to extract from exploring feedback. Well, feedback is a key ingredient, as I told you before, and that's my main focus, but not on the focus of all the people in the project. As may be a key ingredient in the shaping of the scaling relations. I hope I have convinced you about that. It's one of the main drivers of enrichment of the interstellar medium. So if we want to understand how happens the diffusion of metals from the moment when they are producing and at which distance they can be stemmed, we need to understand feedback. It drives the expansion of star formation regions, just pushing them from the outside. It drives the disruption of molecular clouds. You know, the energy that emits a molecular cloud can disrupt them, and this can induce a positive feedback and drive a new star formation and regulate the star formation in clusters of stars. So all this together means that it controls the valence cycle in star-forming galaxies. So it controls how metals are propagated, how they are diluted in the new media that they found, and how the new collapsing of the new molecular clouds could produce a new generation. So the cycle of valence, it's driven by feedback, or it's influenced by feedback. So I'm not going to continue in the list. There are many science cases or physical problems that are totally connected with the feedback. Okay, feedback at scales below 1 kiloparsec. So with that in mind, we proposed a certain time ago, it was approved by Sloan 5 to make this IFU observation primarily focus on the disk of our galaxy. So what I'm showing here is the timing of the survey. In this region here, it's going to is the region that is going to be covered by the first years of the survey, including Orion. I will show you later some Orion data, and the small and large Magallanes clouds. And but apart from that, in the next years, we will cover this enlarged regime. Those regimes are going to be covered in a continuous way, the typical IFU mode. You know, so just connecting one to the other in a continuous way. But apart from that, we are going to serve in a discrete way, like a superMOS, let's say, all these areas in the sky. And this is basically all these points here. This is the timing that for which we have time and we have money. And obviously, we want to also cover the north part of the Milky Way. But the one that is accessible from the North Hemisphere, not in terms of from which hemisphere it can be accessible, but we still don't have the instrumental setup and the money for doing that. So to observe such an area, we need an IFU that is big, really big, okay? And this is expressed in here. The IFU is composed by 3 smaller IFUs that are glued together, and the size of the IFU is similar to the size of the moon. So one single pointing of the local volume mapper samples an area of the sky of the side of the moon. At which cost? At the cost of resolution. So each fiber has 30 arcseconds side. And you may say, well, this is quite a lot. Well, the trick is that the objects are so nearby that basically this side is enough for sampling nearby object that will show you later, like Orion, to a resolution of a few parsecs. And there are other molecular clouds that, other rays to regions that we are going to sample of the order of 10 to 100 parsecs. And of course, the most distant objects we are going to observe of the order of a few hundred parsecs. So we will have different scales with the distance, but that size is enough for sampling our galaxy. Okay. So, okay, that's a summary of what I said to you before. As more distant is a galaxy, as different physical scales you are a galaxy. So, as more distant is that's all habits. Sorry. As more distant is the object that you are sampling, at worst is the resolution you are getting. So objects like Orion, we are going to sample to a resolution of the order of 1.5 parsec per spaxel, indeed, per fiber. And the more distant ones, we will match the resolution, the better resolution that you can get from times and signal. Of course, we cannot observe the same object with different resolutions. We are going to observe different objects with different resolutions. That's the trick, why we sample different scales. And it's a trick and it's a problem. So just to show you, this was the foreseen resolution that we imagine at the moment for the local volume mapper. At the end of my talk, I will show you real data. At this resolution, one pointing of a previous IFU survey that we did, that was made with Muse, requires 81 pointings of Muse just to sample this small area here. That pointing corresponds to half of the size of what you get. No, sorry, it's a bit more on that. No, yeah, it's half of the size of what you get with one single pointing of the local volume mapper. Okay, so just to compare, one shot with the local volume mapper is comparable to 81 Muse pointings and 31 PPAC pointings. This was a previous IFU survey we did actually in 2007 from here, from Palo Alto. And obviously, resolution, the price you have to pay here is the resolution. So all these yellow points here, they are not errors in the image. They correspond to the stars that have been sampled by apogee in the same location. And at the distance of Orion, we will be able to have individual or just 2 or 3 stars per aperture, per fiber. Okay, so we may say that at the distance of Orion, our stellar populations are not stellar populations, are single stars or just a very few number of stars. So at the distance of Orion, we could apply the techniques that are normal down for identifying the physical properties of the stars to the individual fibers that are represented here by pixels. But this could be useful only for these scales. As soon as we go farther away, if this allows me to go farther away, okay, if you go farther away and you don't see the title here, this is another S2 region, and you see 3576. This is a bit more farther away. At this distance, we are not able to resolve individual stars. In each aperture, we will have there are 50 to 100 stars. So the techniques that have been used to identify individual stars will not be useful at this physical scale. We require a different technique, and this technique is what I'm going to explain to you later. That is what we have introduced in the data analysis pipeline of the local volume mapper. The technique requires a development of a different approach in which we don't identify integrated stellar populations, we don't identify single star, we identify something that is in between. Okay. Instrumental setup. Well, as I told you before, the instrument is far more different what we have been seeing previously. It's composed by 4 Röllenstat mounted telescope of 16 centimeters. So we are sampling the universe with 16 centimeters telescopes. These 4 telescopes have different roles. In here, there are 2 telescopes, this one and this one, that are sampling the sky only, to the west and to the east during the observation. Then we have a science telescope, and then we have a calibration telescope. This is only sampling calibration stars. All the 3 telescopes, the 4 telescopes, sorry, have a different IFUs that basically, these are the science one, the one that I showed you before with this hexagon that is divided in 3 sub-bundles. These 3 sub-bundles correspond to 3 different spectrographs. So the 4 IFUs here are glued together in 3 spectrographs, and each of these spectrographs follows the same format, but actually it's the same spectrograph of the one used by the DESI survey. That is a 3-channel spectrograph that sample the spectral range between 3,600 and a bit more than that, a bit above 10,000 astrons, with a resolution that is of the order of 4,000 in the regime of H alpha. And it sample will have a dichroic and that separate the light in the 3 beams. The blue, the red, and the infrared. And all this together is attached to these IFUs that are composed by 1,944 fibers. So it's nearly 2,000 fibers, what is also a lot for IFUs, as you will see later. So now, let's see if this is going to work okay, because always that I try to do that. I'm going to show you some videos of this instrumental setup, and let's see if we have good luck. And I can control that. My God, it's slow. Okay, so you don't see. I will show you. I will stop that and show you how it goes. Now it crashes. Good. Let me see if I can show you again. It should be a play here. No. Good. That's really bad. Okay. Let's come back to here and see if I'm fast. Zoom is eating resources in a crazy way. Well, you see, this is how it operates. Let's stop that. Oh, too fast for me. I will try to do it. Okay. This time I keep an eye. Okay. So this is the spectrograph, the instrument, telescope plus optic. I will show you the optic later. Here is the IFU that is basically pointing to the sky in the east, pointing to the sky in the west. This is observing the science object. You will see that it's tracking in a very slow way. And this one is basically observing the spectrophotometric calibration star. So it's jumping from one side to another. So this is basically how it works. Let's see if I can do. Now I have the bar here, so it can show in a better way. So this is an usual observation. It's jumping to different calibration stars. Okay. Okay, and this is following the tracking of the science point to observe the sky in 2 positions to grab the sky all the time. Okay, so instrumental setup. So the light path, how the light path goes. So this is first is showing you how the telescope, this is the mountain and this is the telescope, the mount, not the mountain. This is the telescope, okay? How it follows different locations. Now there will be the light coming, okay? And this is the optic, okay? So here we have the rotator, the eye view, and the collimator and camera. It's really a very simple setup, okay? So this basically the rotates. It's everything that it does. So the optic is that simple that the efficiency is very high. And that's what we wanted with this instrumental setup. Okay, so let's continue with the presentation. If I manage to go to, it's really going very slow. I don't know why. Is that slow, eh? I don't know why it's so slow. Okay. Okay, let's see. Into live. Okay. So the local variant mapper spectrograph observed, as I told you before, between 3,500 now and 1,000 to a resolution of 4,000. Just to make a comparison, it's the double of the resolution of MANGA, and it's better resolution, spectral resolution than MUSE, and that imposes a problem. With this kind of observation, we can cover from oxygen 2 to sulfur 3, 9,500 angstroms. This is some kind of the most important emission lines that we want to sample, but you may recognize several of them. In the current analysis, where we are getting of the order of 2,200 emission lines per spectra, we want to assess to the temperature and therefore to the and the density in each spatial for H2 regions. So also we want to observe the ISM in the diffuse ISM, not only in the H2 regions. This is the mounting of that we have developed. It's very stable, and that's one of the main keys of making it that way. So nothing moves as the fibers are attached; they never move. That allows us to guarantee that it's going to survive for a long time, because every movement in a fiber may produce micro crashes and scratches that affect to the transmission. Based on the experiment that has been done with MANGA, we are fulfilling the same kind of calibration developed by Renmin Yang for MANGA. We know that we will reach a quality of between 5 and 10% in flat calibration. We have still not reached that value. And the aim is to obtain all the data in the most. The reason for stabilization of the system is to observe everything in the most homogeneous way, so the reduction could produce similar results in different locations. Of course, the galaxy has been observed a lot, and the disk of the galaxy has been observed a lot. So we have a lot of ancillary data that can be used to compare with our results. We have atomic data, dust data, molecular gas data. We have previous observation in different bands in the small and large magnetic clouds. We have, of course, E-Rosetta, so we have X-ray accessible to the same locations, and this will guarantee a multi-wavelength coverage of ancillary data. And the most important ancillary data that we are going to get from the beginning is the data provided by another of the mappers of the SLOAN 5, that is the Milky Way mapper. This is the foreseen density distribution of stars sampled by the Milky Way mapper on completion. Of course, it's still not completed, but it has started before us, and they have already of the order of 1 million stars observed. And all these stars, not all these stars, but our footprint match with the footprint of the Milky Way, part of the footprint of the Milky Way mapper, and therefore we will have spectra of several stars in the same locations that we're going to sample. The difference is that we are going to have a complete coverage, and they are making cherry picking. So they are, well, not cherry picking. They are basically making a selection. So they are not observing all the stars. But this will help us to hint if all our techniques are going to work as we foresee. There is a long way to go, and I don't want to minimize the effort that this requires, because it's a new instrument of which we have no idea of how it will work, and people in the audience know how complex it is to produce a data reduction for an instrument that is well known, and now they give you a new instrument that you have no clue, and you say, okay, let's start making reduction with that. And it's really complicated. So the person in charge was a former PhD, former postdoc of mine, Alfredo Mejia Narvaez, that now has moved to Chile for family reasons, and he's working with Guillermo Blanc in there to finish what we started, the data reduction pipeline. And it's deeply inherited in most of the code from the Berg-Hussmann code, the Pi 3D. People in the audience, I think there are part of your code that is there somewhere. Okay. So first reduction we got something like that. Remember, we have three spectrographs and three arms. So these are the three arms. For experts, they will clearly identify that there are 1, 2, and 3 spectrographs. You know, this is the flat fielding issues that are in here, and this is the gluing issues between the different arms, and this is far, far, far from being in the optimal shape. This was the first reduction that we did. Just to clarify, this was the first spectra we got, and we got that in July of last year on one pointing, and this is not flash calibrated. And as you can see here, there is the transmission curve and the regimes where there is the overlapping between the dicrocks, and that's the same image. We presented that in the Sloan meeting in at the end of July, and just to show you that even in there we can observe the Milky Way star. This is the association of the Milky Way star, and this is the emission of a small Magellanic Cloud nebula. That is this nebula here. Don't ask me which nebula it is. No clue. They give me just a frame, and we spend 1 week to reduce that. But you can see that there is a clear difference in the redshift here, and that's because of the super high spectral resolution. So how we have evolved from there to now? Well, we have not only a working data reduction pipeline, we have also a working data analysis pipeline, and it's publicly accessible. You can download from this link in here. You can go in there and you can work on that. The first person I started to code on that was Alfredo. Then I jumped into that, and it's heavily based on Pi 3D. That was a code developed by Eduardo Lacerda. This data analysis pipeline follows this scheme to explore what is in the data and to extract the data products. I'm not going to go into the details, but basically we decompose the spectra in the emission lines and the stellar population. But in here we cannot talk about population. Remember that we need to talk about individual stars or groups of stars. So the code make a guess of the kinematic composed by the velocity and the velocity dispersion and the dash attenuation of the stellar component, and then it performs a full spectral fitting using templates that I'm going to describe you later. And once you have subtracted that, you have a gas pool spectra from which you derive the initial lines, and this is automatically down fiber by fiber of the 1,000 of fibers we have. Just to show you if this wants to work. Okay, now. Okay, this is a simulated spectra. I will show you later real spectra. They look more awful than that. This is simulated spectrum, and this is the in black. In red is the best fitting with these stellar templates that I'm going to explain you later. And this is the fitting that we get of the different emission lines. And we have run thousands of those simulations. I will show you later plots to ensure that this is working. Okay. And the main problem is, as I told you, how we model this continuum emission without the techniques that we have developed previously of the synthesis of stellar population. And the problem is summarized in this previous observation we took with manga of IC342 that is now published by Barrera Ballesteros, and there are 450 pointings of manga to create this mosaic. This galaxy is as a very particular distance in which one fiber bundle of manga corresponds to 1 kiloparsec. So if you integrate it bundle by bundle, you will have the same kind of image we get with Khalifa, the same kind of spectrum we get with Khalifa. But if you go fiber by fiber, each fiber is of the order of 40 parsecs. So this data for us is very useful because it combines the two sides of the problem. We want to observe things at the resolution of few parsecs, and at the same time derive what is going to happen at the scale of 1 kiloparsec. At the side of one fiber, we can identify individual stars. And by tagging methods, we can derive the physical parameters like gravity and temperature, for example. But at 1 kiloparsec, we need all the techniques of unresolved stellar populations that basically is making a synthesis of the stellar populations and then derive other properties like age and metallicity and so on. So if this is some kind of unresolved stellar population, we tag that as resolved stellar populations, and we get out of the box. So what's the main difference between the use of this thing here is really getting mad to me because, but I'm going to click what I should not. Can I move that? Yeah, good. Thanks. Good. So just to compare the techniques. For generating single star populations, we need a lot of techniques. We need an IMF, we need isochrones, we need a stellar library, and that is combining a synthetic stellar population. And each synthetic stellar population is basically representative of an entire population that is formed at a particular time with a certain chemical composition. And the main requirement for doing this technique is that you need a lot of stars in a single aperture. The number of stars is basically large enough to sample the IMF in the moment of the birth of the cloud. If you don't fulfill this requirement, you cannot apply this technique. That's the message to get. So what we do, okay, we are going to fit with the stars. Yeah, but that's the old way. I mean, the old way the people did that. The difference is that now each star is not a star, it's a characteristic star of a group of stars that share the same physical properties or similar physical properties, and at the same time, the same observational properties. So since you impose these two criteria, the distribution of in the physical parameters is not a single value, it's a probability distribution function. Okay? So from a stellar library, you reduce the space of parameter to a number of stars large enough to make a variable couple of the underlying stellar population at the price that instead of having a tagging of a physical parameter to one star, you have a probability distribution function that could be by model, could be whatever. So just to compare, just to show you here, these are the resolved stellar population that this is done with a double clustering method that I don't have time to explain in detail here, but this is just one particular subsample of one of these RSP templates, and the number here corresponds to the running number. The full template is contains 108 spectra. This is the average of the stars that are included in the clustering, and the shadow orange is the different individual stars that are aggregated to create this RSP. And by propagating the individual PDF of the physical properties of the individual stars, you have a combined PDF for each RSP. So just to put you an example, the star number 14, this one here, okay? The distribution in the projection of the physical parameters, the temperature versus gravity, and metallicity versus relative abundance, it's represented by the blue color. So this blue, well, just to starting from the point, this will be the distribution of the full original stellar library in gray, and in blue is the probability distribution function of only that particular RCP. Okay. For the 38, sorry, that is somewhere here. This is the probability distribution function. Okay. And for the other one, the 47 one, this one here, the probability distribution function here is it's not bimodal, but here you can see it's bimodal. And it's bimodal because you cannot distinguish them. The stars that are included in this RCP are stars that may have a very similar temperature but very different gravities. So we propagate the degeneracies to the level of the PDFs. So in this way, when we combine all these spectra to reproduce the observed spectra, we will combine these PDFs. And if there is a bimodality, the bimodality is propagated, and you cannot escape from that, because in the range of in the spectral range that you are observing, these two stars are indistinguishable. You cannot distinguish them. Full stop. Okay? So,
are those observed stars?
Yes, there are observed stars. Sorry, forget to mention that the library we have selected now is the MASPAR library that contains 30,000 stars that has been tagged with a technique that is named COSA. We make a cut in the signal to noise, so we remove all the ones that have lower than 10 signal to noise, and this limits everything to 10,000, no, sorry, 20,000 stars, 22,000 stars more. That's the original library. Okay, and the first clustering that is made in the physical space, the parameter of physical space, physical space parameter. I don't know, I said wrong. Okay, anyway. Reduce the number to of the order of 2,000. And from there, when you make this clustering in the observed space, you get the number of clusters that this is a number that you can select. You can select 1, 2, 3, whatever. And then we run simulations to understand which is the optimal scale of the SSP. And it has to be a compromise. If you put a lot of templates in the library, the fitting takes for ages, and you are overfitting, most probably. And if you take too few, then the results are not representative. So just to show you one of the simulations that we have run, this is the first step in this simulation is to run the fitting code over the original library. So we have 30,000 stars that we have fitted with this code. The code is not telling you which is the temperature. Of course, this is the average values of the PDFs, but it's telling you all the PDF. So I'm comparing the average value that you get with that and the average value that is in the catalog. And well, I think it's not that bad, considering that here we only use 36 stars. With 36 stars, we can reproduce, for instance, the metallicity. This is a huge dispersion, but the metallicity is going in the one-to-one relation. And that's quite surprising to me. Now it's running the simulation with 108 stars. Beyond that, the fitting time will take for ages, because the spectral The number of spectral points, I didn't say, is 12,000. It's a lot to be processed. But that's for individual stars. Then we made realistic simulations. When I mean realistic simulations, I injected in the simulations all the problems we have with the data now. All the problems with discrete subtraction, the butterfly fielding, the gluing of the different, everything is in there. And I mix with realistic stars. So you take the stars from here and make an average of them. And this is what you get. And you may say, why you don't have a wide range of values? Well, that's because I took the original sampling in the sorry, that's no, I don't want to show you this. No. I took the original distribution, and the original distribution is concentrated in these 2 points. Now I'm running another simulation where the distribution is flat, just to cover all the range. But at least I can say you that this has been made while I'm here, so it's like 2 weeks. Well, actually, this plot I did this morning, so it's and it's not that bad, you know, considering that the data looks terrible by now. But anyway, all this is not the main focus of this project. What we wanted is to recover the initial lines. So in the initial lines, of course, we know that we're going to do more or less okay. So this is the result of a simulation where we have nearly 4 million spectra. Because I took one pointing, this is one pointing in the Rosetta, and I took the residuals of this pointing, so all the crap that we have in the reduction is in there. And I make a simulation with that, taking the output of the data analysis pipeline. This is a map of a portion of the Rosetta. But remember, this is the size of the moon, okay? The white points are broken fibers. We have broken fibers already, and the transportation to Chile, so they are not failures in the fitting. This is the input, if the H-alpha map, an input of the simulation, and this is the output of the simulation on one random selective simulation. So we have 12 of these simulations with different flux scales. We have simulated 1,700, and you will see that there are some missing here, and that was by selection. It was not intentional in the beginning. And we have simulated 199 initial lines. So if you put all together, you have 4 million points, and these 4 million points are in here. This is the 99% contour, 65%, so possibly 1 sigma. So we have a systematic. It's not huge, but it's there, and we need to understand the reason for that in the flux, but not in the equivalent width. So it's something in the relative scale of the initial lines to the continuous. The equivalent width is quite okay. The velocity and the velocity dispersion they match more or less okay. We have a bias in the velocity dispersion. This is the kinematics in here is practically unresolved. So maybe I have to fake somehow the input to reproduce that. And there is a very small range in velocities, but this is the typical thing we're going to have in the Milky Way. So the range of velocity is not going to be huge. Anyway, we can say that it's more or less okay. I have not applied any signal to noise cap. So all these points outside here could be simply lines that are very low signal to noise. Okay. Okay. So this is what we have now. And we are going to deliver, or the code is prepared to deliver all these data products, the weights of the decomposition of the stellar population, the average volumes that I showed you before, the physical parameters, the parameters of the strong subset of velocity, the flux velocity and velocity dispersion for a subset of strong emission lines, 29 emission lines. Of the other 200 emission lines, we are applying a non-parametric estimation of flux velocity, velocity dispersion, and equivalent width. This is very similar of what we have with Pi3D. And all these parameters with errors are going to be provided in a single table. We apply that to the very early data we have, like more than 1 year ago, when we have only one of the 3 IFUs in place. Just to show you how it evolves. This is how the real data look like. This is the Rosetta spectra that I showed you before. Is one spectra, and as you can see, there is a lot of problems. You know, sky subtraction, the gluing between the different light rocks. Okay, it's not optimal. No one expected to be optimal at this level. When you make a zoom, these are real data, is when the marvelous appear, you know, the super high resolution. I mean, it makes that all these defects that you see in the spectrum doesn't matter that much, at least for the strong emission lines. For the ones that we want to achieve, the indicators of temperature is going to be really more complicated. So I make a zoom here just to show you how the program fits. And then I have 3 examples of 3 different fibers, this pointing, fitting, okay? These are real data, okay? This is the integrated spectra in this pointing that I showed you before. Integrated spectra are great to increase the signal to noise when the noise is wide. When you have systematics, it highlights the systematics, and that's what I want to show you. We have still problems in the sky subtraction, in the gluing, whatever that is, I don't know. But then when we make zooms, okay, the fitting goes where it's expected. We can recover the initial lines. Yes, for the fans of temperature, you know, I make a zoom in here. So we did it. We can measure temperature at least using this line. We are going to measure very well 4363, but the nitrogen one is going to be a problem because it lies here. We don't have resin, so it's going to be here, and reducing that is going to be complicated. So just to show you what happens when you put everything together and you start to make mosaics. So remember, each point in here corresponds to the size of the moon. So this is more, as you can see here, is 1 × 1 degrees in the sky. This is the Rosetta Nebula. I show you one of the pointings that I think is that one. And these are the usual strong emission lines, oxygen 2, H beta, oxygen 3, H alpha, nitrogen, well, yeah, it's nitrogen, and this is sulfur 3, just to show you that we can reach. I know that in the audience there is someone that is fan of that line for the strength of the ionization, no? Okay. But of course, we have other parameters. I don't want to, the spectral resolution is that good that we can measure velocity patterns within a nebula, the velocity dispersion patterns, of course, the dust traced by H alpha, H beta, different indicators of ionization and electron densities. Okay. And we are running that for all the objects we have and all the pointings day by day. Okay. So this is an example of the web page. Please don't grab that or they will be going to kill me. And some early science results. Okay. Orion. I think we are all fan of Orion. No? So this is the area that we want to cover at the end of the survey. This is the area that we have already covered. And these are actual data. These are the results from the local volume map. And you can see here the tremendous size projected in the sky. This is 5 parsecs, so it's a good scale. And well, there are many things here just to compare with what we have known before using IFU surveys with Orion. This is the news. Remember, 81 pointings, the PPAC. This is the area that they cover, these IFU surveys. This is one pointing of the local volume mapper. This is the full pointing here. By the way, I didn't say, but in here we combine observations from the local volume mapper, H alpha and oxygen 3 with WISE observations and in yellow, has been cut. Yellow is WISE, just to see that there is a correspondence and we have not made any mess with the data. So this is submitted to publish. For the first time, we can trace the different line ratios in the bubble of expansion of this complex system. We are going to graph, or we have graphed the ionization stage in IC 43, 432, the Flame Nebula. This is the Horsehead Nebula that it's looks very tiny here, but it's there. So this is some of the results that are going. I don't have time now for that because I have consumed a lot of time. Another early result. This is the Large Magnetic Cloud, H alpha 1. Okay, the size of that is really huge, and you see the problems in the reaction. I don't want to say that everything is okay. So I have still not generated the same kind of map because for the different parameters that I showed you before, because none of my computers are able to digest all the tables. So I need to figure out how to do that for the velocity or velocity dispersion or whatever. So guys, and that's all what I wanted to say. I told you there is no big science in here, just a summary of what's going on. We had the first light in February 2020. First light means 1/3 of the issues, 1/3 of the spectrographs. Commission early science happens in the summer. We start to observe the real sugar in October. So far we have observed 5% of the total foreseen survey. We have still not mapped the disk. We have made just the most obvious things, Orion, the Large Magnetic Cloud. We have very preliminary versions of the reaction pipeline, the data IC pipeline, but I hope I have convinced you that the quality of the data is good enough for many of the science that has been foreseen, not for all of it. And there are the first 3 articles have been already submitted, and I need to write the 4th. That's and this is continuing for the next few years. So sorry for speaking so much. I hope you didn't get too bored. And if you allow me, I want to left that tiny image in here.
Okay, we have time for questions. Please, in the audience, Enrique.
Sebastián, thank you for entertaining us with this huge amount of work and data and results that are coming. A couple of comments. What is the role of the porosity of the gas in this transition from resolved to unresolved physics?
No idea.
Okay, so another one.
Yeah, it's there, but I have no clues. I cannot give an answer.
So you said 2 of the telescopes are pointing to the sky, east and west sky, but what do you mean the sky?
Yeah, that's a good question. I knew someone will notice that. Yeah, the gas is everywhere, you know, and so that's the problem. Why subtracting the sky is so complicated. There is a map. I don't know who generated that. I need to there is a map of dark holes in the paths, clean paths in the supposed to be clean paths in the galaxy where you can observe the sky. So we are not observing the sky randomly. It's observing these patches. But anyway, we still detect H alpha. So yeah, it's a problem. So now there is a complete group working just on what, and it was a group that was already thinking about that. There are problems like, for example, the inhomogeneity of the shadow of the Earth when you point to such big distance. That it's also problematic. Yeah. Yeah, it's much bigger than what we have made before. But the experiment we have done based on the ISO modeling of the sky plus a semi-empirical Tupa table that we are generating are promising, but it's still not solved. So it's a big problem. I think it's a problem that You may remember, or you may not remember, that the first spectrum of Sloan have a very bad sky subtraction. And there was one of the biggest development of Vivian White, actually. And the group that was working with, I think it was Kaufman at the moment, made a lot of effort with PCAs and so on to subtract the sky. And that happened when half of the main results of Sloan, the big ones that you may remember, were already published. So I'm not scared about the fact that we still have a very bad sky subtraction. If you see the map for the strong emission lines, we are okay. Obviously, we are not okay for the faint emission lines and for the many things we want to do, but we have a lot of time. So I don't feel the rush. Maybe the other people feel the rush. I don't feel the rush. This will take ages. That's what I wanted to say with this anecdote of human violence. So it takes a lot of time. But we are aware.
Sebas, what you told about the spectral fitting to the individual stars and how you combine them, it seems to me very much similar to what Didier Dulac had already done in the 80s or 90s in the last century. So
yes. The idea is not new. The actual idea that is relevant here is that in all these steps we propagate the probability distribution function, so we can reconstruct the probability distribution function of the population. And how this is connected with larger scales, the only way to know that is to apply to things like this IC 342, and combine the synthetic with the result. And there are people that have tried that with photometry before. So the trick in here is to really keep track of the probability distribution functions. So people combine the stars for subtracting the underlying star population long before the synthetic procedure appears, because it was.
But one of the problems you faced, I mean, it's already there. It's still there. I mean, is that when you are not sampling, since you are using observed stars, you are not sampling the whole space,
yes,
gravity, effective temperature,
yes,
metallicity.
Yes.
So there are very few stars sufficiently metallic.
Yes.
That you are not considering them.
Yes, totally agree. This is a problem that is still not solved. I have presented you what we have on hand. But we need to combine this approach with an approach based on synthetic stars and see if there are differences or not differences. And there should be a trade-off. So I totally agree. We lack of hot stars in here, because if you see the distribution of temperature, then we don't have all or be stars. So it's more fundamental than that. We don't have them, so we need to add them. There are many things that we need first to understand if the procedure works, and advance what we have on hand, and then let's see how this works. Again, I'm not in a rush. If I'm in a rush, you don't establish a project like this. So yes, we will build up on what we have learned from this setup. Anyway, most of the stars, conveniently, we are in the solar neighborhood. So all the bias that are applied to the library are applied to the observables. So contrary to extragalactic targets, where the regime should be larger, most probably we are in the right, apart from the magnetic cloud, right, and the galaxies in the local body. But for our galaxy, maybe this will not be a big problem. Most of the brightest stars are going to be in our vicinity, and most of them we are going to have the same bias as an empirical line. Good for us.
Well, and we hope that with Enrique, thank you very much. I think it's a very impressive amount of work, and the quality of the analysis is impressive too. I just have a question, and it maybe sounds a bit philosophical, but so what is the added value in the analysis of the synthesis? what is the added value of the spatially resolved observations? What is exactly the other one?
Well, actually, as I told you before, all this synthetic analysis is synthesis of star population is based on a lot of engineering, and connecting that to what we really see, that are the stars. There are several attempts, and Ruben did some of those, and he can tell you that it's not that obvious. So we may, or that's one of my personal goals in this survey. We may make a contribution to understand if everything we have made so far is valuable, right, or total crap. I think it's quite an important thing, because we don't know. You know, we hint the properties of the unresolved stellar populations by a lot of engineering. And here you are going to combine the real stars. And then by combining them, all of them, because we are going to get all what is observed. And then we can put together and analyze in the classical way. And then let's see, maybe the isochrones that does not go through the spectrum. And then we need to rethink about it. I don't know, maybe the IMF is totally crap. I mean, so I think it's quite a lot. But this will require more years.
You mentioned different use of CH alpha all over the Milky Way. You can actually have H alpha in the sky, in the Earth sky.
Yes.
Okay. The other thing related to H alpha, you mentioned a series of data that you're using. Using the Wisconsin H alpha mapper.
Yes. Yes. Yeah, I mean, it's not surveying the same footprint, just some patches. But for those patches, in the case of it's good. In the case of the Earth, the heliocentric velocity it's helping in our favor, because this is moving with the Earth and the galaxy, no. So yeah, that's you see from one night to another. That helps.
That means that you have enough spectral resolution. This is a trick for the subtraction. And also for the interstellar medium within the galaxy. We did that at the IAC years ago. There was in the Fecha thesis that it's very difficult to decontaminate by the interstellar diffuse interstellar medium when you do that. But if you have enough spectral resolution, you can.
Yeah, we are still far from that. I mean, the first analysis, it's basically assuming one single component, and so it's very, very simplistic. But the data are there. We will keep updating the data analysis pipeline.
Yeah, well, then you have to correct for the time of the observation, the day, and so on. But that helps a lot.
Yeah.
Sure. Yeah.
You mentioned that in the beginning you were planning to map all the galaxy.
Yes.
But it's not sufficient with the data that you're going to get. Why would you like to map them?
We are observational astronomers. Nothing is sufficient. You know, and when we finish that, we will want to finish with a better spectral resolution and then deeper, a larger telescope. It's a fundamental thing in there, outliers. So you may think about the end of the 90s and the beginning of the 20th century. Everything was clear. Were just some problem with the blue end of the spectrum that people didn't understand, but the rest was, physics was closed.
Yeah, but if you don't have body mapper, what's the advantage of mapping everything with the same instrument?
I still don't know, but I'm sure it's going to be a difference. I mean, the diffuse, how to change the diffuse gas with the plane of the galaxy, and this super bubble. If you see the Rosetta maps, there are so many things that has to be done there. Nothing is enough.
Okay. There is another question in the group. Okay, let me ask the last one. So why do you think that Andromeda can contribute or to improve the result that you will get from the south or the mapping the
Well, Andromeda is unique because it's the only galaxy of this some kind the same size, some kind the same mass, not the same morphological type, but than our galaxy. And it's the only one that is at that distance. So mapping Andromeda will improve our understanding of any other galaxy, not only our galaxy. There is also the advantage that we see from outside. The advantage of seeing from inside is this trick of the distance, that you have different physical samples and different distance available. But it's also a problem, as they have pointed out, it's embedding, our galaxy is embedding everything. It's the only big galaxy that we can observe at that resolution that clearly. The problem is that Andromeda itself is huge. And, the science case of Jamaica was, I buy it completely. The way that they convinced me to enter in the local volume mapper said, no, we're going to sample Andromeda. So, they didn't have to tell me anything more. Now we don't have Andromeda, so you have already, sailing to unexplored waters. But it's there, in my mind, it's there. The Andromeda, in many, many things, from the diffuse ionized gas, to the small H2 regions, to the results, their populations, to whatever, anything, kinematics. We have the same kind of instrumental setup in a slightly bigger telescope, because the resolution, you don't require the same resolution, you require better sampling in the sky. Like, the 2 meters of color out will be perfect for that, and then you sample Andromeda. It will take for ages for digest all this information. So I think all the people in the audience will like it if they. Let's see if it's possible.
Okay, so this is the last day of Sebastián here at the IAA. Tomorrow
I fly back.
will fly back. So it was a pleasure that you stay here for a month almost. We had the opportunity to hear about you and about interesting projects today about the local volume. Also, we had the opportunity to discuss with you a lot of project idea. So thank you for coming, and also thank you for the seminar.
Okay. We did it.